Ever wonder how particles separated by vast distances can interact instantly? Welcome to the world of quantum entanglement. Quantum entanglement, a concept that's as fascinating as it is perplexing. It's a phenomenon that gives us a glimpse into the strange and counterintuitive world of quantum physics. Imagine you have a pair of dice. You roll them one after the other, and each time they land on completely random numbers. Now, imagine if these dice were entangled. This would mean that no matter how far apart they are, if you roll one and it lands on 3, the other will also land on 3, instantaneously. Sounds like magic, doesn't it? But it's not. This is the essence of quantum entanglement. When two particles become entangled, they form a special bond. Their properties become linked such that the state of one particle directly correlates with the state of the other, no matter the distance between them. If you measure one particle, you instantly know the state of the other. This isn't due to any physical connection or signal passing between them. It's an intrinsic link, a deep quantum connection that exists in the fabric of reality itself. Now let's introduce a fascinating theory. It's called ER equals EPR, named after its creators, Einstein, Rosen, and Podolsky. This theory suggests that entangled particles are connected by a wormhole, a shortcut through space-time. It's a bold claim, merging quantum mechanics with Einstein's theory of relativity, two branches of physics that are often at odds. But here's the kicker. This connection, this wormhole, is not something we can travel through. It's not a portal to another galaxy. It's a purely quantum link, a bridge between two entangled particles that exists outside of our classical understanding of space and time. But how does this theory hold up in the face of other quantum principles? Let's delve deeper. See, ER equals EPR theory proposed by physicists Leonard Susskind and Juan Maldacena offers a fascinating perspective on quantum entanglement. To break it down, the ER equals EPR theory is an audacious proposal that links two seemingly unrelated concepts in physics. On one side, we have Einstein-Rosen bridges, more commonly known as wormholes. These are hypothetical shortcuts through the fabric of space-time, providing a direct route between two distant points in the universe. On the other side, we have EPR pairs named after Einstein, Podolsky, and Rosen. These pairs refer to entangled particles, a strange quantum phenomenon where two or more particles become linked and instantaneously affect each other, regardless of the distance between them. Now, Susskind and Maldacena proposed that these two concepts are, in fact, two sides of the same coin. They theorized that every pair of entangled particles is connected by a wormhole. In other words, the ER equals EPR. But what does this mean in practical terms? Well, if this theory holds true, it implies a universe with profound interconnections. Imagine a universe where wormholes are not just shortcuts through space, but also through time, linking not only distant locations, but also different moments in time. Moreover, this theory could potentially revolutionize our understanding of communication and teleportation. If every pair of entangled particles is connected by a wormhole, then we could theoretically use these connections for instantaneous communication, bypassing the limitations of light-speed travel. Similarly, teleportation might not be as far-fetched as it seems, as it could involve simply stepping through a wormhole. Of course, these are highly speculative ideas, and the ER equals sign, EPR theory itself, is far from being universally accepted. There are many challenges and paradoxes to overcome. But that's the beauty of theoretical physics. It pushes the boundaries of our understanding and forces us to rethink what's possible. With this theory, we begin to see a universe where space and time are deeply interconnected. To understand the complexities of quantum entanglement, we turn to the GHZ experiment. Diving into the world of quantum mechanics, we encounter the Greenberger-Horn-Zeilinger experiment, commonly known as the GHZ experiment. This experiment is a shining example of the paradoxical nature of quantum physics, demonstrating the inconsistencies of local hidden variables theories. Let's break it down. The GHZ experiment involves three particles, also known as qubits, that are entangled. This means that the state of one particle is immediately connected to the state of the other two, no matter the distance between them. This phenomenon is what Albert Einstein famously referred to as spooky action at a distance. Now, the local hidden variables theory suggests that the properties of these particles are predetermined, independent of measurement. However, the GHZ experiment debunks this theory. When the particles are measured, the results are not consistent with the predictions of the local hidden variables theory. Instead, they align with the predictions of quantum mechanics. In quantum mechanics, the act of measuring a particle affects its state. This is known as the observer effect. The GHZ experiment shows that when one particle is measured, the states of the other two particles immediately change, supporting the observer effect and the concept of quantum entanglement. This experiment is a cornerstone in our understanding of quantum mechanics. It not only disproves the local hidden variables theory, but it also provides tangible evidence of quantum entanglement. It illustrates that the world of the very small does not behave as we might expect based on our everyday experiences. So what does this mean for us? The implications of the GHZ experiment are far-reaching. It informs our understanding of the fundamental nature of the universe, and it opens up new avenues for quantum computing and communication technologies. The GHZ experiment further solidifies the strange and wonderful world of quantum mechanics. Quantum measurements might seem random, but are they consistent? Let's dive into this fascinating question. In the quantum world, things are not as straightforward as they are in the macroscopic world we inhabit. Quantum measurements, unlike their classical counterparts, often seem random, but there's a certain consistency in this randomness that's quite intriguing. When we talk about the consistency of quantum measurements, we're referring to the way in which the states of entangled particles are measured. This is where the ER equals EPR theory, which we explored earlier, comes into play. You see, in quantum mechanics, when two particles are entangled, their states are intrinsically linked, no matter how far apart they may be. This means that a measurement on one particle immediately affects the state of the other particle. If this sounds strange, don't worry, you're in good company. Even Einstein called it spooky action at a distance. But what's truly fascinating is that this action is incredibly consistent. If you measure an entangled pair of particles 1,000 times, 1,000,000 times, or even 1,000,000,000 times, you'll find that the results are always correlated in a way predicted by quantum mechanics. This consistency is what makes quantum entanglement such a powerful concept, and it's a key component of the ER equals EPR theory. It tells us that there's a profound connection between particles that transcends our normal understanding of space and time. However, it's important to note that while there's consistency in the correlations, the measurements themselves are not determined beforehand. They are fundamentally uncertain until the moment of measurement. This inherent unpredictability is a cornerstone of quantum mechanics, and it's what gives rise to the apparent randomness we observe. So, to answer our initial question, yes, quantum measurements are consistent, but in a very quantum way. They consistently produce results that are unpredictable until the moment they're measured. In the quantum realm, nothing is as it seems, yet everything is as it should be. Quantum mechanics, with its entanglement, wormholes, and consistent measurements, paints a picture of a universe far more intricate and interconnected than we could have ever imagined. To summarize our journey through the quantum universe, let's revisit the key points. We began with the ER equals EPR theory, proposed by Leonard Susskind. This theory suggests that every particle in the universe is entangled with another through a wormhole, a concept that significantly redefines our understanding of space and time. It's as if each particle is not just a single entity, but a part of a vast, interconnected web. Next, we delved into the GHZ experiment, a three-particle entanglement scenario that is a testament to the non-local nature of quantum mechanics. The experiment proves that quantum entanglement doesn't just apply to pairs of particles, but can extend to multiple particles, further emphasizing the interconnectedness of the quantum world. Then we tackled the consistency of quantum measurements. Quantum mechanics posits that the act of measurement changes the state of a system. However, the consistency of quantum measurements ensures that repeated measurements of a quantum state yield the same result. It's a principle that adds a layer of predictability to the otherwise unpredictable quantum realm. The implications of these concepts are profound. They suggest a universe where every particle is entwined with another, where the act of measuring can change reality, and where the outcomes of these measurements remain consistent. It's a universe that is at once chaotic and orderly, random and predictable. As we continue to delve deeper into these mysteries, we find ourselves standing on the precipice of a new understanding. Our exploration of quantum mechanics is reshaping our perception of the universe, revealing a reality far more complex and interconnected than what meets the eye. As we continue to explore the quantum realm, who knows what other mysteries will unravel? Until then, keep questioning, keep exploring, and stay curious.